Okay, so we're still looking at systems of equations, and what I have is 3 examples up here, and I'm not interested as much in the solution of these 3 examples as I am in what kind of system is this. And, we have 2 variables, 2 equations, so they all start looking, obviously very similar to each other. But this particular equation, you could solve it, and you would get exactly one solution, exactly one point that satisfies both equations. Okay, so that point would be 2, 1. 2 times 2 is 4, plus 4 is 8, 2 minus 1 is 1. So we say this is a consistent system. It's consistent, and it has one solution. This is another system of equations, and it is also a consistent system, but the thing is, it has an infinite number of solutions. If you take a look, they are actually the exact same equation. This one times 2 is equal to this one. So there are 2 equations, but really there's only one unique equation. It's a consistent system that has an infinite number of solutions to it. One particular solution could be x is 3 and y is 2. Another particular solution could be x is 6 and y is 0. And both of those pairs would satisfy those equations. Now, it's important to note that even though there's an infinite number of solutions that work, there's also an infinite number of solutions that don't work. So I cannot answer this all solutions because the 0.55 doesn't fit into this equation. It's a consistent system that has an infinite number of solutions, but not all solutions would be the answer to that. The third example is an example of something that I would call an inconsistent solution, or an inconsistent system. If you look at the equation, 2x plus 5y equals 17, 2x plus 5y equals 2, there are no values that make this true. This is an inconsistent system. And regardless of how many solutions a system has, we want to be able to identify which of them are inconsistent. Now, our work with systems is going to basically be with matrices. And so when we look at a matrix, we want to be able to identify, is this system inconsistent right off the bat? And so let's take a look at a couple of examples. So let's say we have 3 equations this time, so 3 variables. 1, 2, 3, and I'll draw this line to divide the solution matrix 4. And maybe this line is 1, 5, 7, 8. And then maybe this line down here is maybe 1, 2, 3, 5. Okay. In this particular matrix, which represents a system of equations, if you look at the first and third row, the first and third row represent the same thing. You have 1x, 2y, 3z, but you have different solutions. Because these are different, we would say that this matrix represents an inconsistent system. And if we recognize that right away, we don't have to solve this. We don't have to go through row reduction to get a solution because we know there won't be a solution. These 2 statements are conflicting with each other. It's an inconsistent system. Okay? Here's an example of another inconsistent system. Let's say we had 2, 4, 6, and 9. And, upon inspection, it looks like they are both, like all 3 rows are different, but if you look closely, each of these have been doubled, but this one is not doubled correctly. So if you recognize that, if everything is doubled but one value, whether it's here, 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 or here, you have an inconsistent system. Another example of an inconsistent system would be something like this. If you look at the first row and the second row, they're different, they're not multiples, everything is distinct. And this last row says 0x plus 0y plus 0z equals 2. Well, in other words, 0 equals 2. Again, not a true statement. This system is inconsistent. Okay? Now, what happens if you have this? So you have 3 rows, so 3 variables in this augmented matrix. And if you take a look, row 2 is exactly row 1 doubled. Okay, so it's not wrong math. Everything's been doubled correctly. But this is an example of a consistent, it is consistent. And this consistent system will actually have an infinite set of solutions because you really only have 2 distinct equations. This equation is merely the first equation times 2. And it'd be exactly like the situation we had earlier when we had 2x plus, 2y equals 6, and you could have maybe 4x plus 4y equals 12. Because everything is doubled. Okay? So there are an infinite number of solutions here. This is exactly represented in this particular case because this row is double that. This is consistent. It has an infinite number of solutions, but the key is it's consistent. Okay, take a look at another example. Let's just start over. What if I had 1, 0, 1, 3, and 1, 0, 0, 0, and 0, 0, 1, 5? Okay, so it's been partially reduced, it seems, to get into row reduced echelon form. And we take a look, there are no multiple rows. This row may be a concern for you because I see a lot of zeros with a 1, but actually it's fine. This says 1x plus no y's plus no z's equals 0. In other words, x equals 0, and that's fine. That is consistent. And these are okay because now it tells me that z equals 5. And then obviously if I know z, I can go back and solve for x. So this is consistent. And you should be careful because, and almost I guess anticipate, a singleton number with a whole bunch of zeros is okay as long as this is not that singleton number. If you have 0, 0, 0, some other number, then that would be inconsistent. This is perfectly fine. This is consistent. Okay. Maybe one more. What if it looked like this? 2, 3, 4, 0, 1, 1, 2, 5, 0, 0, 0, 0. Okay. Again, 3 equations in 3 variables. These 2 rows are not multiples of each other, so there's no issue here. The issue you may think about is this row right here. Does that make this system inconsistent? 0x plus 0y plus 0z equals 0. There's nothing wrong with that statement. 0 equals 0. This is a consistent system. Okay? It is a consistent system, and there are an infinite number of solutions because in reality, I only have 2 equations with 3 variables. So there are an infinite number of ordered triples that would satisfy this solution, but it is consistent.